Okay, so graphs of rational functions. We're going to do this mostly by hand. So the book gives us like 8 steps to do. You don't have to memorize this. I think most of this sort of intuitively should come to you if you do enough of these. So I don't want to go through them one by one right now. Let's see. Want to highlight a couple of things. So it says here, step 4, test for symmetry. I never really do that. So I don't think it's something that you have to do to be able to graph it. Asymptotes are important. And then I told you we're going to do this by hand, so we don't really do step 7 either, although occasionally if it's a word problem we will. And then use the results to graph it by hand, so we're going to basically do this thing by hand. Okay, so let's just look at it. So the reason it says analyze and graph is because we can't just go ahead and plot it in a bunch of points. We're going to analyze the function a little bit, look for some asymptotes, some vertical, some horizontal, maybe some oblique asymptotes, and then we're going to work our way through it until we get the graph that we want. So what do we do here? Well, let's start by factoring, because clearly we got some stuff here that factors. So what do we have? Whoa, that's really bad. Let's see if I can make a slightly straighter line. So x minus 3, x plus 3. And then here 9 and 18, so x plus 3 and x plus 6. Okay. I'm not going to simplify right away. I'm going to start by looking at the domain, because the domain includes everything that I have in this thing over here. So x plus 3 and x plus 6. So x plus 3 can equal 0, so x cannot equal a negative 3. And x plus 6 can't equal 0, so x cannot equal a negative 6. So I have a limited domain. So now I'm going to look at this one more time, and instead of just looking at the domain, I'm going to look at it in its simplified form. So because I have an x plus 3 here and an x plus 3 there, it cancels, and so I get x minus 3 over x plus 6. So that's the reduced form of this function. That means that the negative 6 here, that is a vertical asymptote. What happens here when you have a factor both in the top and in the bottom is that you're going to get a hole there. There's a hole in the graph. There's a hole at x is a negative 3. I would like to know what the y value is at a negative 3. Okay, so I'm going to pretend that you can plug it in, but I'm going to use the new function in there. So I'm going to use r of x in its reduced form, and I'm going to see what happens if I had been able to use that negative 3, because if you could reduce it and just use this one, then you would have had the following: negative 6 divided by 3. So at a negative 2, we get our value. Or we get our hole. So the hole will be at x is a negative 3, so the hole will be at a negative 2 for our x, a negative 3 for our x, and then the y value for the hole is at a negative 2. I think that's it for the bottom. Let's see. Next thing then would be, so we did vertical. Let's see, what do we have for horizontal and oblique? So let's check. It's an x squared and an x squared, so the degrees are the same, so it has a horizontal asymptote, and all I need for that is to look at 1x squared divided by 1x squared, because the functions when x goes to infinity, keep in mind that this goes for when x goes to plus or minus infinity, they act like, this function will act like this. Well, and that just means it's going to approach 1. So y equals 1 is my horizontal asymptote. Okay? And I think that pretty much takes care of it. Is there anything else that I need to do? I don't think so. Right, so then the last part obviously is sort of sketch what you have. So at this point, I know the following things. I know that in a negative 3, negative 2, I should have a hole. Negative 3, negative 2, I get a hole. I know that there is an asymptote at x is a negative 6. So negative 3, negative 4, negative 5, negative 6. So So there was a vertical asymptote at a -6, and there's a horizontal asymptote through 1. And I do need to check something else. I need to at least do my intercepts. So let's check intercepts. And after that, I might be able to graph the whole thing. So what happens when I use 0 on the function? So I get a -3 divided by 6, which is a -1/2. So at 0, I'm just below. And how do I solve for 0 here? And again, I'm using the reduced form here. So x minus 3 divided by x plus 6 is 0. That occurs when x minus 3 is 0, so x is 3. So there's a 0 at 3. So my intercepts are in blue. So on this one, I feel pretty confident. I feel confident doing this. This is going to go approach over here. So we'll make it go a little bit further. And then it's going to approach over here. So now most likely I'm going to get a dot at -7. I'm guessing I get my dot somewhere over there. But I don't know this for sure. So what you can do then is just check. So let's check f -7 and see what you get. So a -7 minus 3 divided by a -7 plus 6. So -7 minus 3 is a -10 divided by a -1. So actually I get my dot at 10. So that means that it's coming from here and it runs this way. Okay, so that dot's not really accurate, but that doesn't really matter because it's mostly just a sketch. Okay, and then that would be it. Alright, let's do one more of those. So how about if it's x squared minus 1 over x? Okay? So start the same way. X plus 1, x minus 1. There's no way to reduce this thing. So in terms of my domain, I know x can't equal 0, so that means I get a horizontal asymptote, a vertical asymptote. At 0. The degree in the top is 1 bigger than the bottom, so we can, we should probably see what the oblique asymptote is, because it's 1 bigger in the top. I do have one, and fortunately for me, this is just an x. So you know what? You can literally split this way. So this particular function can be rewritten pretty quickly. X squared divided by x is just x, right? Minus 1 over x. So that means that the oblique asymptote is going to be right there. Y equals x. Right, what else do we need? We've got domain, vertical asymptote, oblique asymptotes. Let's check for intercepts. So intercepts are usually a good thing to check for. So what happens at 0? So at 0 I am not allowed to use that, right? Because I would get a -1 divided by 0. So that was not allowed. And the other one is, when is this function 0? Well, that would be easiest to spot out of this one. So if that's the function, it's only 0 if the numerator is 0, so either x is 1 or plus or -1. So I do have two intercepts, one at a positive and one at a -1. Now, I think I have enough information to graph this particular function. So I get a vertical asymptote at 0. Okay, since I can use colors, it makes my life a little bit easier. So there is an asymptote right there, and the other one's oblique, and it's the line y equals x, so that's that 45 degree line. So it goes through here, goes through there, It also goes through here. Let's try to get one more in there. One more reasonable dot. Okay, so I have another asymptote that runs a little like this. I have intercepts. I have one at a -1. I have one at a +1. I don't cross here, right? You never cross a vertical, so I really don't have any choices. I mean, it has to be this. It has to do something like this. And on this side, it approaches over here, cuts through there, and then it does that. So, and if you don't feel comfortable with that, then you can plug in a couple points. For example, what would happen if I used f as a -2? So at a -2, you would get 4 minus 1 is 3 over a -2. So the -2, you can see that I'm in the negatives. Okay, I'm not quite to a -2, but and you can do the same thing over here with a +2 if you're not sure. So what happens at a +2? You would get 4 minus 1 is still 3, and then you just get 3 over 2. So yeah, it works. Okay, and you can see here that symmetry would have helped me a little bit, but yeah, not a huge fan of symmetry. I think it has its uses, but to have to do it every time, I don't think it's really necessary. Okay, so there's my graph. Alright, let's go backwards now. What if I gave you a graph and you had to come up with the function for this? Okay, let's see, I have red. Alright, that will work. So that's a vertical asymptote, right? So if it's a -5, then x plus 5 should probably be in the denominator, and at x is 2, then x minus 2 should probably be in the denominator. Okay, so far, here's what I have so far: x plus 5 and x minus 2. Because I have a horizontal asymptote running at 2, that means that the degree in the top is equal to the degree in the bottom. And the leading coefficient in the top could be like a degree in the top would then be, in this case, would be an x squared. Since the bottom right now is an x squared, but then that needs to be a 2x squared. So tentatively I can do this, 2x squared in there. Okay? So what else do I have? Well, this is my guess. But I'm struggling a little bit with what's happening over here. So how? And then the reason I'm struggling with that is because I get the same end behavior here. You can see this one and this one. I don't have the same end behavior. And I haven't actually looked at something else here, and that's intercepts here and there. So what do I do with those? Alright. And I do have an intercept here, but that's a little bit harder to see. So if x is a -2 is a 0, then I'm going to need an x plus 2 in the top. So in the top I need to change a couple of things. Okay, I still need an x squared, right? But I'm probably going to have to rewrite that in terms of some factors. So I'm going to say that I need an x plus 2 in the top. And then because this one cuts through at 5, so that's another intercept, and then that means that I have an x minus 5 in the top as well. So do I still, so far I still feel pretty good about this. The other thing is that because this is a double, so it's a 0 but it's a double, that means that I actually have this number twice. So I need an x plus 2 squared. So now I need to have an extra one over here, and that brings me back to to this thing over here. That brings me back to the double asymptote there. So if a double 0 gives you a 2 here, then an asymptote that's being approached on both sides should probably count as a double asymptote. So I'm going to argue that x minus 2 needs to be squared as well. And if x minus 2 is squared, then that balances this thing again, because now I have an x squared and an x, so this is an x cubed in the top, and I'm dividing by an x cubed in the bottom. So they cancel each other out, and then 2 over 1 gives me that horizontal asymptote at 2 again. So that's it. I think that's going to be my guess. My best guess is that this is a function that would look a whole lot like that if I graphed it. Okay? So if you wanted to check that, I guess I do have GeoGebra open. So let's see if I can get rid of that one for now. So what did we say? We said that it was 2, in parentheses in there, so 2, and then x plus 2, and that one was squared, times x minus 5, and that whole mess is divided by x plus 5 times x minus 2 squared. And let's see. Does that look like the picture that we were working on? That looks pretty good. Okay. So you see that it is possible to piece it together. It takes a bit of work, but you look at all the things that you would do if you had to graph it, and then you just go backwards. And then the tricky thing here really was that we had these doubles here. So this double here, that's tricky, and then this as a double asymptote. So you got to keep those things in mind. Double asymptote. I guess what I didn't check here was whether or not it was increasing and decreasing in the right direction, and I lucked out. I mean, it's a positive too, so this thing is positive on the right. Not very positive, but is positive. And somehow it's still positive over here. Not sure what that means. Okay, last problem. Let's say that we have a aluminum factoring, or a can aluminum manufacturer. So each can has a half a liter. The top of the can is a special alloy, so it's a little more expensive than the sides. And we want to express the cost of the material for the can as a function of the radius r. Okay, so the can has a rectangular area that's folded, and then 2 circles on the top and the bottom. So the cost will be the area of these 2 things. So the cost is going to be 2 times pi r squared plus 2 pi r h for this thing over here. Well, unfortunately, well, that's not the total cost. That's a total area. Unfortunately, I still have an h in there, so I got to deal with that. Let's see, and I also have to deal with the cost. So the cost is 0.05 cents over here if r is in centimeter, at least centimeters. So it will be this times 2 pi r squared. Well, that's good. And this one, and that's the one that we're struggling with a little bit, because I have an h in there, and this whole thing needs to be a function of r. So let's at least multiply this out. So that's 0.1 times pi times r squared plus 0.04, if I do my math right, times pi times r times h. Okay. Well, we do have a restriction here, and that is that the volume of the can is 500 cubic centimeters. And the volume for a can would be the area of the base, pi r squared, times the height. And we know that that volume has to be 500. And so we can actually rewrite this thing in terms of h. So h is 500 divided by pi r squared. So now we have an expression that we can plug into the part that we didn't really like. Oh, sorry about that. So this can go in here. So here's my total cost function. It's 0.1 times pi r squared plus 0.04 times pi times r, and then h is actually 500 divided by pi r squared. So that can be cleaned up a little bit more. So the cost as a function of its radius is 0.1 pi r squared plus pi cancels. The r squared cancels with the r, and 500 times 0.04 is 20. So 20 over r. And we're going to write this as one rational function. So the denominator here should have been r. So to make this an over r, I need to make this an r squared. So it's 0.1 pi, sorry I said r squared, but I need to make that square cube, plus 20 all divided by r. So there's the function that represents the cost. I do need to make sure, of course, that the radius is larger than 0. Okay, well that's it. Use a graphing utility to graph the function. Alright, using a graphing utility to graph the function. There's the function. So for some reason it's not letting me. There we go. So we're going to show it. So there it is. Well, it's a little hard to see there. So let me zoom it out. So that's the function. Graphed. What value of r will result in the least cost? Well, keep in mind I don't really care about this part. So we're going to get rid of that. So and then the least cost would be right there, which is a minimum in this case. So minimum, what do we want? Function is f of x. Start value, let's start at 0. The end value, well, don't really care. At least if I just go to 10, I'll catch it. So there we go. The minimum occurs at an x of 3.17, and then it'll be 9.47. So 9.47 cents apparently is what the cost is. And that's it. Okay, thank you.